Hi, in this video, we want to take an initial look at working with aerial data for spatial statistics. Okay, so aerial data, what we've got going on is that I've got polygons and I have measurements for each polygon region, and I want to be able to use this for my statistical modeling. So in the previous videos, we've taken a look at how do we handle this when I have points on the ground. And we assume that we have a continuous surface, from a math point of view, continuous. Now, what we're going to be doing here is that instead of having individual points on the ground, I have some, polygons, geometric regions, such as neighborhoods, counties, states, countries, something like that. And I want to use the measurements for each of the known regions to develop a statistical model. Okay, so there's going to be two big things that we have to worry about when doing this. Before we even get started, we have to worry about these two things. Is that how do we say which regions are considered neighbors of each other? And after that, what is the weight of the influence in our statistical modeling as we do our model fitting? All right, so this example is taken from Applied Spatial Data Analysis with R, Chapter 9, Modeling Aerial Data. Here are the names of the authors of the textbook. Here is its website, and you can download the book for free through UCF's library. All right, so first thing we're going to do is we're going to load our data. So to run through the examples, we're going to take some 1992 census regions for the state of New York, and we're going to take 11 hazardous waste sites. Okay, and so I've got a shapefile. I'm going to load it with read OGR from the RGDAL package. Pull that in, easy peasy lemon squeezy. Then I've got another one. All right, so this is for the census regions. This part of the code is for the hazardous waste sites. I'm pulling in, once again, using the same function, read OGR. Now, what we're going to do, we're going to pull in a neighbor object, which is stored as a GAL file. All right, so something about this is that there's multiple formats, multiple softwares for storing neighbor objects. Different softwares, different packages do things differently. This chapter of the textbook, 9.2, actually covers how to cross and connect between them. I'm not going to go too deep into it. I'm just going to, just go a touch into it and then move on. All right, so here we're getting the neighbors. So this tells us what are the neighbors of each of the census regions, and we're using SPDEP. So this is going to be the big heavy hitter package for aerial data, and we're doing read.gal. And you'll notice to make sure everything matches up right, I'm pulling the row names from my spatial polygons data frame that I've already loaded in. And then here I'm pulling in the major cities of the region that we're interested in, using, once again, read OGR. All right. And in all these data sets, the projection, the default projection, looks pretty good. So I'm not going to mess with it. I'm happy with what we have. All right, so let's go ahead and visualize what we've got. So we're doing spatial statistics, very natural to make a map. So let's go ahead and just drop the census regions into the SP packages version of plot. Let's go ahead and add some text and some labels on there, taking the coordinates of the cities to specify where the cities are. Here we're slapping down the names from the cities to appear on the plot. And the author went through and has two plots next to each other, and this A is just to specify it's the first one. I went ahead and just went through. I thought about keeping this out, but it's a good example of using the bounding box to set up things for like your margin and to be able to put additional information on there. And so here we can see where the major cities. We're going to be focusing on Syracuse for this. And now let's go ahead and visualize the waste sites. So I'm going to take my census polygons, and I'm going to take the waste sites. I'm going to put them down as points. And then we'll go ahead and put down the names of each of the sites. And this position specifies where is the actual label in relation to the point. So a 1 puts it below, a 2 puts it to the left, a 3 puts it above, 4 puts it to the right. And this bounding box trick just enables me to put a B in the plot. And so here we can just see where are each of the hazardous waste sites. All right. All right, so when we're doing statistical modeling with aerial data, there are two major things I have to get worked out before I can even start. And that's going to be which regions are neighbors to each other and what are the weights between neighbors. Okay, so this is going to absolutely have a huge impact on everything that comes afterwards. So if I make a poor choice on this, there's going to be repercussions down the road. The author recommends that if you don't know, go with binary weights of zeros and ones. If they touch each other, they're neighbors. Another reasonable choice would be to go with like inverse distance weights, something like that. So what is typically done is that if they're not close or touching to each other, then what we're going to do for the regions, we're going to say they're not neighbors. Now, something that we could do possibly is if I have two polygon regions that are close, but they're not actually neighbors, there's like another region in between them, we could still put them as neighbors. That's a possibility in this, and that's okay. Another thing to consider about this is that the weight aspect of being neighbors doesn't have to be symmetric. So we have some flexibility in how we go about this. However we proceed, however we choose, will have a major impact on what we get for our model. So, this is not to be taken lightly. Now, if you want more information on what, how to tackle this with the SP-DEP package, we can use a vignette and just NB with SP-DEP, and it'll come right off. If you run this code in RStudio, it'll pop up in the help document section to the lower right-hand corner. All right, so let's take a look at neighbor objects. Oh, now something that I want to point out is that we're going with the international spelling of neighbor. We're not going with the American spelling. So there is a U in there. And this is true when we have our keywords inside our function. So you'll notice I'm not spelling neighbor the American way. I'm spelling it the international way to be consistent with the keywords inside the functions. All right, so the neighbor relationship between in observations are represented by an object of class NB. They're basically a list of length n with an index number of the neighbors of each component. And so for the first region, the first entry of the list is going to be integers of all of the neighbors of that of the first region. And so the 10th list item, it corresponds to the 10th region of interest, and then all the integers indicate which regions are neighbors of the 10th region. All right, so now if an observation has no neighbors, then the component contains an integer 0, something to be aware of as you work through this. Now, something that needs to be reiterated with this is that if A is a neighbor of B, B does not have to be a neighbor of A. So it's, kind of funny that way, but that gives us that flexibility. If we want, there's plenty of ways to make sure that we have a symmetric relationship if we choose to do that in this. And so the neighbor object also contains attributes, typically a vector of character region identifiers and logical values indicating whether the relationship is symmetric. All right, so let's go ahead and just, take a look at the number of regions for the neighbor objects. Let's check the cardinality of each neighbor's region. So if I go with the SP_dep_cards function, this gives me the cardinality of the neighbors. So if I see a 0 here, I know that that region, the corresponding region, has 0 neighbors. And so here, just scanning, I can see that there's a 1, and scan real quick, I see that there's an 11. Gives me an idea of what I'm working with. And if I want to, I can summarize. Now here, the summary function is actually coming from RGDAL, not from SP_dep. That surprised me when I was working through this. And so here, we get the summary information. We see the number of regions, number of non-zero links, percent of non-zero weights. So notice that that's a very small number. Typically, when we're dealing with neighbors, we're going to have mostly, so if we count 0 as the weight for non-neighbors, we're going to have a lot of zeros. Here's the average number of links. And here we have an idea of what's going on. And if I choose to print, it's very similar to the summary function, but a little bit truncated. All right, so now let's go ahead and visualize the neighbor object. So here I'm going to go through, I'm going to plot all of the polygons, and I'm going to plot the borders as gray because that's not the main emphasis of my plot. And then I'm going to plot in black the neighbor connections. Now to do this, something I'm going to do is I'm going to plot the coordinates as points, and then we'll go ahead and make connections. And so here we can see, going by the center of each of the polygons, we can see like which regions are neighbors of each other. There's a lot more regions in here than I expected when I first looked at this. All right, so now what I want to do, I want to look at a subset only for Syracuse, around Syracuse City. So what we're going to do is I'm going to take my spatial polygons data frame, and I'm going to subset it so that only when the area name is Syracuse City, and I'm going to make a new sub spatial polygon data frame. Now for my neighbor object, I'm going to take my neighbor object, I'm going to subset it just like I did before, and here I'm using the subset function. And now here I get a new, smaller sub spatial data. And we can see that number of regions is 63, number of non-zero links is 346, percent of non-zero weights is 8.7. So we definitely have an increase there. So we have less sparsity. Average number of links is 5.5. All right, so let's create a neighbor object on the Syracuse data. So first thing I'm going to do, I'm going to grab the coordinates for the spatial polygons. I'm going to grab the names so I know what's going on. And now here, I'm going to do k nearest neighbors to a neighbor object. And inside, I'm going to go k nearest neighbors. Now k is equal to 1. All right, so what we're going to do, I'm going to find the closest neighbor for each region. Okay, so why is this good? Well, one thing that this will do is if I look at this, I can look at the maximum distance between neighbors on this, and they'll tell me the minimum distance I need to have to make sure that if I say that distance is what it takes to be neighbors to each other, that will be the minimum distance I need to make sure that every region has at least one neighbor, which is important in my modeling. Now here we can go with 2 neighbors for k-nearest neighbors. Here we can go with 4. And there's advantages and disadvantages of each of these setups. All right, so now what I want to do with k equals 1 and the distance between neighbors, I want to find the minimum distance that I could set to be. So what I'm going to do, I'm going to say if 2 regions are within this distance of each other, then they are neighbors. So even if they cross over another border, I'm going by distance instead of actual sharing a boundary to be called neighbors. All right, so here what I do is I find nearest neighbor for each region. I find the distance between them. Then I take the maximum of those. Because remember, at that maximum is the, that's one region to its closest neighbor. All right, so if I go lower than that number, what's going to end up happening is that particular region will not have a neighbor in my modeling. And so this distance here that I get is the minimum distance I need to set if I want to use distance to determine neighbor relationship. All right, and so how I do this is I take my neighbor with k-nearest neighbors 1 object. I've got my coordinates for Syracuse. I'm going to unlist it. And then by taking the max, I get that. And now here, if I want to use distance for nearest neighbor, I can work through this and choose what I want. Now you'll notice that 0.75 times the max will be less than the max. This will come up later. All right, so now let's talk about spatial weight objects. So far, we've taken a look at how do we decide if 2 regions are neighbors of each other. Now that that's established, with the ones that are neighbors, we want to have a non-zero weight. So anytime I have 2 regions that are not considered neighbors, I will have 0 weight between them for my statistical modeling. What I want to do now is decide what will be the weight between 2 neighbors. And remember that the weight of A influencing B and the weight of B influencing A does not have to be equal to each other. So it does not have to be a symmetric relationship. Weights between neighbors do not need to be equal. All right, so the author recommends that we use binary weights when we don't know what's going on. So if I've never worked with this data, never worked on this type of problem, you know what, I should just go with binary, 0, 1 weights and keep it simple and run with it. Definitely a good way to go. But that's actually not the default. The default is to do row standardized, where we have all of the weights add up to 1. And so in binary, 1 if the regions are neighbors, 0 if they're not. So this will be a symmetric relationship. All right, so neighbor to list W function takes neighbors as a list object and converts it to a weight. The default setting is W, where what it does is after we get all of our weights for each individual region of interest, we average out what the weights are after we establish who are neighbors. And so it standardizes to a sum of 1. This is also called row standardization. And so we have multiple ways that we can approach this. Is that B is basic binary coding. W is row standardization, so weighted average. C is global standardization, so sum over all links to N. U is equal to C divided by the number of neighbors. Sums over all links to unity. S is variance stabilization. And then min-max. And min-max wasn't really talked about too much in the help documentation, so I don't have anything to say. And so here, let's go ahead and just run default so we know that this is going to be row standardization. We get our output. And we know in the object, we have the style, we have the neighbors, and we have the weights. Now, just to see what it would be like if we ran other ones, what I can do, just to do something like quick, fast, and easy like, I went ahead and ran this function with a whole bunch of different styles, all the different possibilities, and this just shows what we get. So the order is BWCUS. So beware I cuss is what. So here we have binary. So binary has, let's see, average number of links is 5.5. Then W row standardization has 5.5. Looks like 5.5 will be pretty common. So these are coming out pretty similar to each other. This S0 and S1 and S2 are different. And there's advantages and disadvantages for each of these, depending on what I'm working on. And this last one is for min-max. And we can print the object with the print function to see what the list W object is. Now, something we can also do is that I can actually specify the weights myself if I want to. So let's say I have subject matter knowledge, or I want to use a specific type of modeling, or the client wants me to do something in particular. Then what I do is I specify in the glist parameter what I want for the weights. All right, so for this example right here, right now, what we're going to do, we're going to compute the range of inverse distance weights, and we're going to summarize the weights, and then we're going to check that the sum of weights is equal to 1. And so here, I'm taking the range of the cardinality and 1 over that. We can see what we get for that. See that it sums to 1. Now, if I can take a neighbor to list weights with a binary, I can compute that real easy. So I'm getting binary weights on my Syracuse data set. And you'll notice that I have all ones. Now with the inverse distance weights, what we're going to do, I'm going to get the distance between regions using this function nbdis here. It works out all the distance. I specify what's my neighbor object, specify my coordinates, and takes care of the rest. And now I'm doing inverse distance weight, but I'm also multiplying by a scalar. And then right here in the glist, I put my inverse distance weight into there, and it works out. And this will give me what I actually want. And so now I can see what are the range of my non-zero weights. And we see we have an average of 1. All right, so now let's go ahead and visualize the 3 spatial weights. And so to do this, I'm going to kind of blow past all this code because it's just kind of slugging through it. All right, so I have 3 inverse distance weights. First thing I want you to look at is the binary one. With the binary, you notice that it's an all or nothing. Either I've got a 1 or I've got a 0. Now, if I look at the inverse distance weights aspect, and so The B is just to specify that it's a symmetric relationship on this. What we see is that, actually, no, it's not symmetric. Nope, it is not. So notice how I have a difference here and here. If I look at the colors, there is a difference between those, and that's because of the reweighting of things. And then here, I can look through, and we can see that when I look at this part, I can see that this is also not symmetric. All right, so now one thing we have to be mindful of is that if I have a region with no neighbors in this, I can start having errors. So SPDEP does this to make sure I don't do something I don't want to actually do. That if I have an empty neighbor object, then what I want is SPDEP really wants us just to get rid of it or to assign a neighbor to it. And so what will happen with default settings, if I try to work on things, specifically neighbor to a weight object, it's going to throw an error. And you notice I'm using a try function that is to not have R shut down when I get this error. So this code here gives me an error because this has an object, a region with 0 neighbors. And the system doesn't like that by default. So with 0 policy equals false, I'm going to get an error. What I can do, if that's okay, I will still want to proceed, even though I have 1 or more regions without a neighbor. I can set 0 policy equals true. It's still going to be a pain in the neck because a lot of functions are going to be like, whoa, 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 I don't like this, I don't like this. And so, playing around, I would, if it's not going to disrupt your modeling, I would make sure that all regions have at least 1 neighbor, just to get the code to run. And just be mindful if you had to make a choice for computation regions rather than for modeling regions. And so here, when I do the print, I have to put down the 0 policy again. Otherwise, I'm going to get an error and there's going to be problems. All right, so now let's talk about handling spatial weight objects. All right, if you read 9.2.3 in the textbook, they talk about like different functions, different packages for connecting between different softwares, different packages. I'm going to skip over most of that just because I felt like some of this was rather specific, and if you need that further information, you know where to look. All right, so if I was to go through and set up a matrix to represent the weights, most of the time that matrix would be a sparse matrix. So we would have mostly zeros. All right, so this is especially true if I'm going to be doing the binary neighbors aspect. Now, when we deal with sparse matrices, R has some special functions to work with, and the DGR matrix setup will take care of this nicely for us. All right, so here, what this function is doing, it's taking our weights, and then it's going to convert it over to a sparse matrix format. And you'll notice in the sparse matrix format, instead of printing a 0, it just prints a dot. And so that makes it easier for us to read when I have a large matrix. So anytime I see a non-zero entry, that indicates that those 2 regions, the one that, so this would be regions 199 and region 1 are neighbors to each other. And there's a lot of output for this, so I'm just going to scroll right on past. Now we can so let's say that I've got some weights. They're not symmetric, but I want them to be. Well, what I could do is I could just take the average of the matrix with its transpose. Easy peasy lemon squeezy. And the list W to U does that for me, quick and easy. And so if I run this on a weight object, it will return a symmetric weights for me. And if I need a matrix from it, I can drop that into the matrix function we just looked at. All right, so we looked at how to go from weight object to matrix. Now I want to look at how to go from matrix to weight object, go back. And so here, if I take the matrix to list W function, if I drop a weight matrix into it, it will automatically convert that to a list W object for me. And so here we can see the outputs. And so this is literally just taking what I had previously. Here is that sparse matrix we looked at a moment ago. So I'm converting this to a matrix on this step. And then on this step, I'm just converting it back. Now, some things like attributes can be lost in this process, but hopefully we can recover that manually. And if I want to convert the lines between neighbors to a spatial lines data frame, that's easy peasy lemon squeezy, because I just need the neighbors to lines function for me. And so here's a visualization of the Syracuse neighbors. And so we can see that there's a, one neighbor here is just connecting, one region here is connecting to one neighbor like that. Now, this section of the textbook talks a lot about different file formats and different softwares. And this part is talking about that. So if I have a GAL file, I can read that using spdeps read.gal. And here, this is true function is just checking to see, do I actually have the same objects? And yes, I do. Now, if I have a GWT object for my neighbors, then I can use the read.gwt to neighbor function in spdep. And then I can check to see, are these actually the same? Is my neighbor and the GWT object input the same? Yes, they are. All right. So now we want to just touch very briefly, very quickly on simulating spatial autocorrelation. All right, so something that's going to be a big deal, and this will come up in future videos, is this matrix here of identity minus row times W. So I is identity matrix, rho is the autocorrelation coefficient, and W is the weight matrix. Now, this matrix, we don't have to necessarily invert it, but it must be non-singular. And we're going to use this to simulate autoregressive processes. And so here's just kind of a quick way to do it for simulation. I'm going to do a random number generation. I'm going to figure out the number of regions I have, generate some numbers. I'm going to specify the autocorrelation, and then with this function here, I'm going to drop in the weights, the autocorrelation coefficient. That gives me this, and then I'm going to use matrix multiplication with the random number that I have generated. Now, something that's going to be important about this, when we look at this, is our spatial lag. So remember that we have lag in time series data for what's the how far back do I consider for correlation aspect? Well, lag is going to be very similar, but now it's going to be a little bit more complicated because I don't have a set distance between my objects. And so since I don't have like a set fixed amount, I need to use those weights to take this into consideration. So the lag is going to be the sum of neighbors times their weights. And so that is the lag at that individual region. And if the weights are row standardized, then we're going to have a weighted average for our neighbors. And so here we're just going to go through and do some plotting, standard stuff. We're going to use lowest because the author just wanted to use lowest. And so here we can see that when I have uncorrelated random variable, here I have a correlated random variable. It's not crazy strong correlation, but it is there. And we are using this lag list W to specify what the Y coordinate is for each of these. And the randomly generated numbers are representing points on the ground that I've measured. Well, that's all I've got for you. Take care and goodbye.